following session, Why Teach Astronomy, will be presented by Ms. Rebekah Roundey, who is a science teacher at Faith Lutheran School in Plano, Texas. Please welcome Ms. Roundey.
As I said, there are handouts over there, but they're not essential things. So, why teach astronomy? Because space is cool. Thank you for having me already. I didn't think I could get away with that. Unfortunately, or probably fortunately, our classical model begs us to be more intentional in that in the subject we teach. I teach astronomy as a 12th grade class, so this presentation will be geared towards teaching astronomy as a high school class, but hopefully, even if you're looking at adding or improving upon an elementary or middle school astronomy course or unit, there'll be information in this presentation to interest you. So, why teach astronomy? There are several reasons one might think about adding astronomy at the high school level. Perhaps there's specific student or teacher interest. That's why we first offered it at Faith. A handful of students requested it. One of them is here right now. And I was very eager to try teaching an astronomy class. Another reason you might have is this is very tempting at a classical school because it's part of the quadrivium. Teach astronomy, check that box off in the liberal arts, call it a day. Perhaps the school requires 4 years of science, and there are some students who just aren't going to cut it in AP Physics, so they need an easy science class to finish out their graduation requirements. Astronomy deserves better than this. Astronomy is remarkable in its own right, as it is the oldest science, the newest science, and has been the driving force of advances in physics throughout history. For an educator, astronomy is beautifully suited to be a capstone class to finish off 4 or more years of classical science education, as it unifies observation, scientific methods, logic, theology, and myriad other subjects that students have studied so far. So we first need to clarify the distinction between classical astronomy, what is being referenced when you see classical writers placing astronomy as one of the seven liberal arts, and modern astronomy, what the science is now. And I'm using science in the modern terminology of science, not in the classical sense of science as a body of knowledge. The art of classical astronomy in the broadest sense is making mathematical observations to collect data about the heavens and place it into a system. Historically, the focus of these observations was the stars. This includes the planets, the sun and the moon, and how they move against the background of fixed stars. The system was a model of the heavens, and whatever model was used had to be able to make suitable predictions of future motion. So to make this more clear, we're going to have a crash course in the basics of classical astronomy. I need you to pretend that you are an ancient Greek philosopher. What that means is that maybe you don't have a lot of formal education, but you sit outside, you look at the world around you, and you try to figure it out. When I tell my students to think like philosophers, they know it means to turn off the side of their brain that says, I know this because I learned it in science class, and only consider the things directly in front of them. So hopefully you'll be able to see this. This is just a simulation because we can't just go outside and look at the sky right now. So you're sitting as a Greek philosopher watching the sky, and you know that every day the sun rises in the east, it crosses the sky, let's make it go faster, and sets in the west. And every night the stars arc in a dome over your head. What do you think is the most sensible arrangement of the sun, the moon, let's get the moon for now. The sun, the earth, and the stars. So, the simplest arrangement would seem to be a sphere. You have the earth at the center, all the stars are on the outside of the sphere, and then the sun going around the earth. Do you agree that this accounts for what you just saw? Perfect. So over time, you see that there are 2 types of lights in the night sky. Let's get back to being nighttime again. There we go. There are stars that stay in the same position relative to each other, though on a nightly basis they move east to west. These you call the fixed stars, and it's easier to keep track of them if you assign them to picture pictures, or constellations. These just provide a roadmap for you in the sky, because you notice that there's another type of light that moves at its own pace. These you call the wandering stars or the planets. I'm not able to show those easily here because it doesn't set up with the time. Altogether, you count 7 wandering stars, 7 of these planets, each with their own distinct appearance and rate of motion. You have Mercury and Venus, fastest moving and never far from the sun. You have slow trudging Saturn. You have very bright Jupiter, and you have blood red Mars, and then the very distinctive sun and moon. Classically, the sun and moon are planets. You see it over weeks and months that these planets don't move just anywhere in the sky. They always stay on a certain path. So I have here a picture. All of these lines are the path that you see the planets traveling along through weeks and months. Let's call that path the ecliptic for reasons that are beyond the scope of this course. It's a good deal harder to see, but the sun does also follow this path. You have to see what constellation is in right at sunrise or sunset. So you take this information and you add it to your mental model of the cosmos. You have the planets moving in circles in front of the ecliptic. And it seems to make sense that the slower the planet moves, the farther away from Earth it is. So you order them accordingly. It's a very nice mental model, and it's very easy to visualize that the objects in the sky should travel in perfect, uniform circles. Perhaps it's their natural motion, what they want to do. You should be able to figure out where the planets will be at any time in the future. Except the planets don't move consistently. All of them, at their own times, will appear for a few days to stop moving against background stars, move backwards before pausing and resuming their forward motion. This image shows exactly that happening with Mars. These pictures are taken from August of 2022 to March of 2023, showing that zigzag motion. What does this do to your model? Well, let's say that somehow you are an ancient Greek philosopher shepherd who has a toy spirograph. We all know what spirographs are. Okay, good. I don't need to explain them. This gives you an idea. Let's say now in your model, each of the planets has a little circle that it travels on as it goes around the big circle. This is perfect. Your model just needed a little tweak to be able to explain your observations and now be able to predict where the planets will be next. And it still fits with how they should obviously be uniform circular motion. You know, for example, that Mercury makes 3 of these retrograde motions per year, so you can figure out when they will be. Except, then you notice the sun doesn't move at a consistent speed. Sure, on like a daily basis, it moves east to west at a consistent speed. But on an annual basis, where it's moving against the background stars, at some points in the year it's moving quickly against the fixed stars, and at some points in the year it's moving slowly. So you, and by you we now mean 2nd century astronomer Ptolemy, come up with 2 little fixes to this model. One, you make the orbit of the sun eccentric. That is, the center of the orbit is not actually the Earth, but a little bit to the side. And 2, the sun in your model now changes its speed. This is a problem because you would really like your model to have uniform motion, so you add a hypothetical point called a gateway point. Kind of a mirror image of where the Earth's position is, and if you were standing right there, then the sun would appear to move at a constant speed. It's messy, but it makes decent predictions most of the time. We could keep going and add equal points for the planets and an explanation for why Venus and Mercury are never far from the sun, and all sorts of other little adjustments that are necessary to determine things like how far above or below the ecliptic the planets will be at any given time. But as much as I would love to give an entire presentation on classical astronomy, that's not what I promised in the presentation description. Classical astronomy sought to make accurate predictions of celestial motion. Accuracy in predictions was needed for astrological purposes, for timekeeping, for religious calculations. For example, to be able to compute a table of the date of Easter for years in the future, you needed a model which could accurately calculate the dates of equinoxes, and a model that could accurately calculate the lunar cycle. On top of that, regular calendar adjustments needed to be made to account for the uneven number of solar days and a solar year. In the Arabic world, significant advances were made in astronomy due to the need for knowing hours of prayer and for needing to know what direction was Mecca from any given location. Astrologers needed what was called ephemerides, tables of where each planet would be when in order to make their predictions. When Ptolemy wrote the Almagest in the 2nd century, it was this need for prediction which motivated his models, and he was willing to sacrifice some of the beauty of his models for the sake of good predictions. This does bring us to one of the greatest distinctions of classical astronomy. There's a heavy emphasis on instrumentalism in their study. That is, the models proposed are not meant to describe the actual real motion of the heavens. Their merit comes only from how useful they are in making predictions. In a modern astronomy course, the huge wealth of material covered in texts, such as the Almagest, typically makes up a single introductory chapter. For one, the Scientia, the body of knowledge associated with astronomy, has expanded incredibly even in just the last century. The existence of galaxies outside the Milky Way, composition of planets, nuclear processes in the sun, these are just some of the Scientii,
Scanty eye, yeah.
thank you. It's been a while since I did Latin. That have been discovered in only the last 100 years. But also since Copernicus and Kepler and Galileo, modern astronomy has sought to describe how the heavens actually really are. Not just how the planets move, but why they are moving. What the planets and stars are made of, even what space itself is. Modern astronomy is now the study of the universe, defined by its subject matter and by its goal of realism rather than prediction. So, does this mean that to teach astronomy classically, we need to teach an instrumentalist, geocentric astronomy? No. Learning the Scientia of classical astronomy is historically interesting, and the mental exercise of understanding the geocentric model is good practice, but that isn't what makes an astronomy class classical. While it's important to understand the difference between what classical writers are referring to as astronomy and modern astronomy, I don't think we necessarily have to make a distinction or begin teaching astronomy. Just teach astronomy. Teach astronomy as an art. Teach the Scientia, including modern developments. Teach the history of astronomy and how our understanding of the cosmos has changed. Teach the methods of studying the heavens, and teach the tools, both the modern tools and the tools of antiquity. You can admire this beautiful picture. In an astronomy class in a classical school, observation, scientific methods, logic, theology, and more can be unified. Certainly these things are potentially present in any science class, but astronomy naturally provides a web to connect seemingly disconnected areas. A few basic observations might have literally cosmic implications, which bleed over into other subjects, giving students opportunity to apply tools from their other classes. As an example of these intersections, we'll walk through how it was discovered that the Milky Way was just one of many galaxies. This is a discovery which took place 100 years ago this year. There are some stars known as pulsating variables. They change their brightness on a regular, periodic basis. In the late 19th century, enough observations had been made of these pulsating variables to to find a relationship between the time it takes to go from bright to dim to bright again, that is, the star's period, and its actual peak brightness, or its absolute magnitude. Once astronomers measure that time for a given variable star, they know how bright it is. This is incredibly useful, because if you know how bright something is, and how bright it appears to be from Earth, you can calculate the distance. You do this all the time without thinking about it when you drive at night. You know how bright cars' headlights are, you see how dim they appear, and you make an estimate of how far away it is. Well, you can do that with much greater precision in astronomy. So soon after this, pulsating variable stars were found in what at that point was called the Andromeda Nebula. It was believed to be a dim cluster of stars not very far away. But by using this relationship between the period of the variable stars and their brightness, it was found that these stars are not dim nearby stars, but incredibly bright, incredibly distant stars, 2.5 million light years away, which is far outside of our galaxy. So far, we have stayed soundly in the realm of astronomy. We've made observations, we've applied scientific reasoning, but when we reach this point in class, there's many diverging topics. Consider just the implication of realizing our galaxies are unique. We also get a set of a very interesting logical problem. Premise: the Andromeda Galaxy is 2.5 million light years away. This is based off of measurement of pulsating variable stars, and has also since then been confirmed by multiple independent methods of measurement. Premise: if something is 2.5 million... Okay, I didn't think of that correctly, sorry. If 2.5 million... You can just read it. If something is 2.5 million light years away, light from that object will take 2.5 million years to travel from the object to the observer. This is given that the speed of light is finite and constant, and the definition of a light year. Conclusion: the light from the Andromeda Galaxy has taken 2.5 million years to reach us. You should all have your doctorate alarms going on. We have to take from outside of science that the universe is significantly less than 2.5 million years old. From pulsating variable stars, we have suddenly come to a theological concept. Now questions are raised about the limits of human observation and reason, the apparent conflict between the book of nature and the book of scripture, how both of them are interpreted. Astronomy has a very special knack for forcing students to closely examine their worldviews. I've had many students tell me afterwards that such an examination led to a strengthening, ultimately, of their biblical worldview. One of the best parts about having astronomy as a senior level class is that students are prepared for these intersections. This is not by my doing, but by the excellent work of my colleagues. They come to my class with their doctrine sound and their logic sharpened. In discussion, they argue their points efficiently, thanks to their rhetoric classes. After years of reading great books, they are well prepared for the readings I assign. One I particularly like is Galileo's letter to the Grand Duchess Christina, in which Galileo defends his faith and attempts to justify apparent contradictions between his observations and scripture. Students are able to engage with Galileo's arguments and frequently end up disagreeing with him on some points. With a solid mathematical background, they can venture into non-Euclidean geometry and consider the implications of positive or negative curvature in space-time. After years of being reminded that science has limitations and can only apply to the physical, natural world, we reach cosmology, the study of the structure of the universe. And there we have the difficult task of working through which questions are answerable and where exactly is that boundary between the natural world and the supernatural. A study of astronomy necessitates a study of the history of astronomy. This complements the history that is being learned in other classes and also provides vital context to their previous science education. For example, the shift from classical astronomy to modern astronomy is best understood within its historical context, a context that includes medieval philosophy, works of the Renaissance, and the Protestant Reformation, just to start with. Historically, astronomy has been the driving force of physics, motivating developments such as Galileo's new distinctly non-Aristotelian view of motion. Newton's Principium was written in large part to provide mathematical justification for the planet's elliptical orbits. William Herschel's discovering infrared radiation while observing the sun led to the entire electromagnetic spectrum. The study of the solar spectrum that was begun by Fraunhofer motivated two chemists, Bunsen and Kirchhoff, to study atomic spectra. They eventually showed that elements could both absorb and emit specific wavelengths of light, and this led to modern atomic models such as the Bohr model. Even nuclear physics owes a great deal to astronomers' careful probing of the sun's composition. In teaching astronomy's history alongside astronomy itself, students gain this context to their previous science education. It's one thing to see an example of inertia, or demonstrate Newton's third law of motion. It's an entirely different thing to see where those laws came from, what came before, and how they were developed. All science classes are built off of cultivating wonder, but I believe that astronomy is the best at cultivating wonder and humility. Rather than trying to explain this, I'd rather demonstrate. You may have seen this picture before. This is the Hubble Deep Field. It's assembled from 342 separate exposures taken by the Hubble telescope over 10 days in 1995. The small area of the sky that the telescope was pointed at appears to the naked eye to just be dark and empty. Imagine holding a pin, a sewing pin, out at arm's length. The area of the sky covered by the head of that pin is the area of sky in this photograph. Those specks of light, the little tiny ones all through the background, are not individual stars. Each one is a galaxy. Over 3,000 of them, each containing anywhere from a few thousand to a few trillion stars. This looks almost the same. It's the Hubble Extreme Deep Field. It focused on an even smaller portion of the sky in a completely different direction than the Hubble Deep Field. It covers about 1/30,000,000th of the whole sky. It is the deepest image of the sky ever taken. Again, the bright flecks are not stars. Each one is an individual galaxy. In this picture, over 5,500 of them. This is what you may have seen before. This is the pale blue dot. This photograph was taken in 1990 by the Voyager 1 probe as it passed beyond the orbit of Neptune. Before the cameras on the probe were permanently shut down, they were turned backwards to capture one more image. That speck of blue, it hardly shows up on these, right there. I need to point it out on this one too. So, wait. Barely a pixel. If you are over the age of 35, you are in this picture. What were you doing on February 14th, 1990? I think no matter your worldview, pictures like these leave one a little breathless. From a secular worldview, they may provoke humility by demeaning humanity. We are nothing but occupants of a mote of dust around a normal sun in a normal solar system, hurtling through space surrounded by trillions of other similar galaxies. But within our Christian worldview, we get to experience a very different sort of humility. One that stems from a realization of God's glory and His love. What can we do but quote the psalmist, "What is man that you are mindful of him, and the son of man that you fear him?" Poetics aside, astronomy also serves to cultivate humility in a far more practical way. Have you ever tried to schedule a telescope night? The sky does not care about your plans. There will be clouds on the night of that major celestial event you've been hyping for weeks. Your noble plans to have students do 20 observations per quarter will have to be altered due to weeks of poor seeing conditions. You will learn to humbly accept things that are beyond your control. After a lot of shaking your fist at an uncaring sky. So, what does this classical astronomy actually look like in the classroom? There's not yet any high school level astronomy textbooks written with the classical model in mind. If there are any quality Christian high school level astronomy textbooks, they have escaped my searches. What does direct instruction look like? Are there labs? What's our homework? What's our goals? As a disclaimer, I am still working on figuring this out, but this is my work in progress so far. In terms of a textbook, I think it's very important to remember that the textbook is not the curriculum. The textbook is a part of the curriculum. Certainly you do not want a textbook that you are fighting with constantly, but understanding the textbook as just one of the resources in your curriculum frees you from having to find a classical textbook or even a Christian textbook. Recently, I worked with our school board to select new astronomy textbooks. My priority was an information-dense but accessible text. I view the textbook as a reference book for the scientia I expect students to learn, not a syllabus for how I teach the class. Regular observations serve both as labs and as homework. We start these observations right away in the first unit, when students are learning the celestial sphere, much as we covered at the beginning of this presentation. However, there's a vast difference between being told the stars will move in a certain way, or even being shown it on a computer, as you were, and actually going out and getting those observations. These observations have to happen over long periods of time, so we must start them early. I'm working to utilize a format of observational logs described in an article by Philip Sadler on observational journals. I did put information to that on your handout. I think you can find it free online. This whole next paragraph is really just summarized from there, so when you look it up, there's information. In one sense, observations are the regular homework in the class. The students must set aside time on their own to complete these observations. We begin with very specific assigned observations, some of which we may complete in class, such as measuring the altitude and the azimuth of the sun throughout the day. Then they are assigned observations such as make consecutive nightly observations of the moon for a week, or make regular observations of the sun at sunrise, or sunset if better suited to their schedule. These assignments are intentionally left open-ended, with the student having to determine on their own what make an observation means. The grading for now is equally flexible based on completion. But then we have guided group discussions, talking about what patterns were visible, what patterns should have been visible, what observations would they have to make to confirm those patterns. The goal is that over time, the student shifts from broad qualitative observations to planned quantitative observations. They do this by repeatedly redoing those sets of observations, getting more data, or in some cases less, as they realize that they reported extraneous or unnecessary information. And these observations don't stop at the first unit. As I said, it takes time for the stars and planets to be in optimal viewing conditions. The skills to use the observation equipment takes time to develop. The background stars are always changing throughout the year, so there's always new things to be seen. And you'll soon find that a single school year is not sufficient to make all these observations. Drawing from the idea of classical astronomy, I definitely provide students with tools and devices that work in their models to make useful predictions about the sky. Are you familiar with planispheres? Perhaps. Planispheres, they allow the user to see which constellations are going to be visible at what time for any night of the year. These are indispensable in planning observations or learning your constellations. There are planetarium software, such as Stellarium, that's what I was using at the beginning of the presentation, that are very good for this purpose, and I encourage students to use them. But I think the physical nature of the planisphere helps cement the cyclic, regular motion of the sky. There's similarly moon calculators, which you can use to find what phase of the moon is going to be present when it's rising and setting out for any day of the year. There's one with a very classical connection. People know what this is?
The Christmas ornament.
We're going to need a really big tree branch to hold that. This is an astrolabe. It is essentially an analog calculator for the sky. It can function slightly as a planisphere, partially as a clock. These go back to medieval times at least. I haven't tried this yet with students, but I'm really hoping that I can teach them to be comfortable using an astrolabe, and then we read through Geoffrey Chaucer's treatise on the astrolabe. I just think they're cool. But also, just like using a slide rule builds a mathematical number sense, I believe using these tools helps to build a sort of space sense. In case you're wondering how one might manage to purchase all these devices for students, yes, one can get planispheres and astrolabes, but there's also wonderful websites that I have put on your handout of places that have free downloads, and you can print the basically templates necessary for assembling your own planispheres and astrolabes, moon calculators. When I'm working on figuring out, I found designs for building your own sextant for measuring the angles between celestial objects. I haven't gotten it quite to work yet. I don't know if it's user error or poor design. Back to practical examples. I forgot to move the slide around. Okay. If at all possible, students should be practicing with telescopes. If your school doesn't yet own a decent telescope, try to take steps to acquire one, either permanently or perhaps on loan. This does require a teacher proficient in using the telescopes, which takes time, but it's a very rewarding activity. My eventual goal is that my students are skilled in setting up, using, and taking down telescopes within the first quarter of the school year. This also makes it able to help me run telescope nights, which are open to school families, when the weather permits. This has led to some very fun days in class where they practice assembling and disassembling the telescopes. And then I turn off the classroom lights and make them repeat it with a more authentic experience. A solar filter obviously allows for solar viewing, but it also allows practice and use of the telescope during the day when the students are at school. And if the telescope is at this time out of the question, they are not. Astronomy has been done for thousands of years without them. The possibilities for interdisciplinary connections are endless. Follow Eratosthenes' method of measuring the size of the Earth. Exercise geometry by finding the relative shape and size of the sun and moon. Translate some Latin texts. Delve into historical debates about the shape and size of the galaxy. I like to incorporate what I call flashback Fridays into class. These are possibly just 5 minutes, maybe an entire class period, in which I focus on some area of the history of astronomy. I'm considering assigning topics to students so that they can prepare their own flashback Friday presentations as well. This past year, to combine a lot of their science classes, my astronomy students had the opportunity to build their own pinhole cameras and use their chemistry lab skills and the optics they learned in physics to expose and develop photographic paper. This was for the purpose of strengthening their understanding of the optics of the telescope and light gathering power. And of course, all of this is at the same time being woven into direct instruction of the scientia of astronomy. The knowledge of the solar system, stellar power, galactic structure, galactic classification, and the like. There may not always be direct correlation between, say, what a student is working on in their observation logs, what they're learning, or whatever test is coming up, and the skills that they're practicing, such as using a telescope, but the overarching art of astronomy will meld these activities into a coherent course. So, why teach astronomy? Beyond its scientia and tools, astronomy provides connection to the rest of students' education and challenges them to put the tools of their education to use. Its long history provides a thread which ties together much of the history of science and makes it an excellent capstone science class. The subject has expanded far beyond what it was historically, but we can see why astronomy deserves its place in the curriculum and why it still deserves a place in our classical school. Thank you. I believe there's plenty of time for questions. Yes?
May I make a comment?
Please.
So it also ties a lot into music and how we understand harmony.
Yes.
I wrote my senior thesis on this. I'm really excited. So essentially the way that the universe and the surrounding galaxy, the whole universe, I guess, as a whole, works with harmony also ties into God's idea of order and that everything has a perfect order. And so within that, we know that music and good music that kind of emulates God and himself is in harmony and in good order. So when you are encouraging the study of astronomy, you're encouraging the study and the use and the goodness of order in itself, which then leads into harmony, which then leads into music, and it kind of just all ties itself back together.
Absolutely. And one of the cool things about talking about the order of the universe is also finding places where the order isn't quite working. Why do we have 364.2, however many point is it here, 0.28 days in a solar year? Like these things that you feel like they should have been nice integer numbers. Why is a lunar month 27 point whatever days? Places that you feel like there should have been nice numbers that just offset.
Maybe you're just a Pythagorean.
Maybe all of creation is growing out. Any other questions? Yes.
Do you teach stars are still forming, or do you have them challenge that question?
It's something we talk about the models that have been proposed for stellar formation, and we also talk about the arguments against those models. I think it's always important to teach what is being studied in science and use it as a starting point of how does this interact with our worldview. Does that answer your question?
It starts the question.
Oh no. Was there another question? Yes.
I have two questions.
Okay.
The first one is, how do you observe the stars in DFW? Do you drive out of town, or do you try to do it from within town?
You have to go like 50 minutes north to get to a decent viewing location. It's hard. It is almost impossible. There are some stars you can see, and you start to find locations that work better. So going into like 20 minutes east, and the sky gets more clear. I keep having all these dreams of planning an astronomy camping trip, and that sounds exhausting to plan.
Might have more luck convincing the government to shut down their lights for a couple of days.
That'd be great. Somebody wants us to do that. Yes.
Are you willing to share your ordering of quadrivium with astronomy at the top? Because I've also heard music as the final capstone as well. Do you have an opinion about why astronomy finishes it?
I'm thinking of astronomy as a capstone, not necessarily to the quadrivium, but to modern science education. I don't have an opinion yet about the ordering of the quadrivium. Yes?
We're not, contained only by public school schedules, but how much can you really do during the summers and during these nice months where there's clear nights, to get this done? What have you personally done? I mean, Texas is nice during the whole year.
Yeah. We have decent weather throughout the whole year, which is very nice. I think at some point you have to accept that astronomical observations are sometimes painful and miserable. I have in my observation log all these notes in the margins like, did Kepler get eaten alive by mosquitoes? I'm hearing coyotes in the distance. I didn't find my body. I died during astronomy. But yeah, winter is often a very good time for astronomical observations because the colder air makes for better seeing. but then you are cold. I don't know if that answers your question. I think it's just you find what time you have and you make use of what is visible. Which, if you live in a large city, might not be a lot, but fortunately, there are a surprising number of constellations that can be visible even in very light polluted areas, and it can almost be easier to learn the constellations with light pollution, because if you go out to the middle of nowhere, there are so many stars, you can't pick out what's what, but the brightest stars are recognized as part of the constellations because they're the brightest, and that's what we see in more light polluted areas, so there's some purpose, I guess. Yes?
I would say, just in the city, you do actually live your planets better than you do otherwise because they stand out.
Yes. It can be hard to track their motion.
Yes, you can.
But they stand out really well.
Do you have suggestions for somebody like in elementary or junior high grades kind of prepping for this sort of thing? Like if there's a unit on astronomy, like are there terms or certain skills that are good to get you on so that when we get to this level they're more ready?
Probably. So when I do an astronomy unit in 8th grade, I'm focusing mostly on the celestial sphere, so I'm going to pretty much just work through the first unit of my astronomy class and talk about the vocabulary, ecliptic, zodiac, all the... It's nice to talk about the solar system, but I really want them looking or being aware of patterns in the sky, like daily, monthly, annual patterns. I don't know if that's necessarily the best option, but it's what I've been going for lately. Yes.
Just not directly astronomy related, but you said it's the capstone of your science program. What order do you guys do your science in the high school level?
Freshmen and sophomores alternate between biology and chemistry, so all the freshmen and sophomores will take biology one year, and then all chemistry the next year. They do junior year physics and then senior year astronomy.
Can I ask a complicated question? I've heard that the 7 liberal arts create an artifact. What artifact, like logic makes statements, grammar makes sentences. What does astronomy make? Like maths?
I mean, I guess classically you could say it makes predictions, it makes models. I don't know how that would translate as well to modern astronomy. I haven't thought about it from that perspective yet.
You mentioned something about space sense. Could you say a little bit more?
Oh no, you called my bluff.
Could you just explore that a little bit more in terms of what that would mean regarding being alert to have a space sense?
Processing. A little bluff. I'm not sure how to explain that. I was thinking about how when you use a slide rule, you are thinking about numbers in a different way. It allows you to be able to just roughly use numbers differently and think about how they interact and how these physical things, because you're seeing the whole sky at once on a planisphere, and it's showing you how one part is visible in part of the year, not the other part of the year. That's giving you this bigger, broader picture that you can then use for your more narrow need. Which doesn't really answer your question of how does that connect to being an art. No, can you give me a year to answer that? Okay, I kind of put together the phrase space sense, and now I have to actually think about what that means. Any other questions? All out early and can go stretch and enjoy the summer. Oh, there's another question. Okay, more questions. You don't
Not
need
a
to
question, but an experience. I had a better understanding of what's really going on when I was attempting as a teenager to pick up objects in the sky through binoculars.
Yes.
And no matter how still I held the binoculars, sooner or later that thing is gonna move across my field of vision, and I'm gonna have to chase it. And it's like, oh, yeah, right, moving, duh. And it got me interested in trigonometry. Got me to understand what parallax really means, why we have binocular vision, and why that's really useful to not bump into things and make our depth perception. And, but, so even if you don't have, I live in Michigan where it's just cloudy all the time, so, if you say, we won't have any class time to go out and look, but get a pair of binoculars, find out what the three powers are on it, and take measurements and focus on something and see how long it takes to go across it, because it's going to move, which it's not easy to notice just by the naked eye. And it gives you that space sense of, wow, I have to follow this.
Right, I love that when students are looking at the telescope possibly for the first time, they look again and they say, the moon moved, or the star moved. I'm like, and you just see this dawning realization that they know that the Earth is turning. They just haven't processed it yet. You had a question.
Have you looked at Memorial Press's astronomy curriculum?
Is it high school?
Third grade or sixth grade, or it's elementary? But I'm wondering if you had a...
I haven't looked at it yet, because I've mostly been focusing on high school astronomy.
And it goes kind of with Greek mythology, and there's some fun little phrases that you get to memorize. Like last night when I was walking back, I saw the Big Dipper, and I said, "Oh, Arctic tourists, speed on despite that," and little things like that that were just nice to teach younger kids.
Yeah, I think the goals of having astronomy as a younger grade class are going to be very different than as a senior level class. I mean, you're not going to be having intense theological discussions with third graders of the same sort. But
there's a nice vocabulary list in there with ecliptic and zodiac and all of that too for the next one.
What was the computer software you were using at the beginning?
Stellarium. Wait, no, I think I put it on the handout. Yes. It's a free software, and then it has a web version as well. It's fantastic. You can put in any location and see exactly what the sky will look like from that location any day, any time.
No Google Space, we have Google Earth.
Give them time, you'll see that Google card.
Do you think have you ever made use of planetariums, especially in bigger cities? Are they receptive to teaching harder knowledge to older kids, or is it just younger kids?
I haven't looked into that yet. It's something on my to-do list, but not very high on my to-do list, unfortunately. I think that probably they would be very eager to work with whatever age levels and class to bring.
If you're close enough to Wichita, the Cosmosphere, it's really great, and they'll do higher end.
Bit of a drive, but it's noted. Yeah. Yes?
Do you think with the astrolabe you're talking about space sense, do you think that has something to do with having sort of a God's eye view of, I can rewind time, I can look at the entire frame of time possible, just like with the flick of my wrist, I can see, it's like a whole view of the entire sky and the entire possible time.
Yeah.
Do you think that has something to do with it?
That makes sense with what I was trying to think of. You could see if I am looking at it this time, here's what it looks like, but I can move it to a different time and see what it would look like then without having to wait 6 months. Yeah, that explains it.